The StreetFox Recumbent Trike is a fast and comfortable version of the classic Tadpole-style trike, two wheels in the front, which includes rear suspension, three-wheel braking, and 26-inch rear wheel for optimal gear range. The StreetFox looks and handles as well as many commercially produced trikes and can be completely built using commonly available and inexpensive bicycle components and some square tubing. Not one single machine part is required. The StreetFox also includes an adjustable bottom bracket, so it can fit riders of just about any height from 5 feet to well over 6 feet tall. Due to the rugged construction and use of sturdy 14mm axles, 48-spoke front wheels, the StreetFox can accommodate riders over 250 pounds. There is plenty of room for customization due to the simple monoboom frame, so you can alter the design to suit your own style or needs. The entire rear portion of this trike is made using an unmodified stock rear triangle from a typical suspension mountain bicycle. As shown here, you will need the complete rear triangle, the suspension spring, and at least the small part of the main frame that contains the tube that connects the rear triangle to the frame, allowing it to pivot. The front part of the frame used as parts is not important, so it can be in any shape as long as the rear of the frame is perfectly functional. Since you can purchase a basic bicycle for not much more than $200 from a department store, I decided to work with new parts, as this would ensure the suspension, wheel, and brake parts were all in perfect working order. If you decide to find a used bike or scavenge the local dump for parts, ensure that the rear brakes are working and that the rim is not damaged in any way. One of the main concerns when designing a Tadpole-type trike is how to connect the two front wheels to the steering components. The obvious answer would be to simply find a pair of typical 20-inch front wheels, then move the threaded hub axle to one side so you can bolt it to something strong enough to support it. This answer is partially correct. The problem with this approach is that a typical bicycle hub will not have an axle strong enough for connection on a single side, and your axles would bend as soon as you enter the first corner or before you even make it to the end of your driveway. Sure, you could probably build a kid's trike using the largest mountain bike hub axles you can find, but this would still be a risky design, as the first bounce up a curb would certainly bend the axles. Another factor in choosing trike wheels is their lateral strength. Since a trike cannot lean into the corners, the two front wheels are going to be under massive stress around any corner at higher speeds. For this reason, almost all Tadpole-style trikes use 20-inch or 16-inch front wheels with at least 36 spokes due to their excellent strength. You may be thinking that this project calls for a pair of expensive rims mounted to a set of custom-made hubs, but the good news is that you can purchase a pair of sturdy 20-inch trike wheels from any bicycle shop in the form of 14mm axle, 36 or 48-spoke BMX wheels. Unless you have an unlimited budget, or really know the dynamics of bicycle wheels and plan to make your own hubs, the BMX wheel route is the best way to go. You can expect to pay between $100 and $200 for a pair of suitable wheels complete with smooth tread tires from a bicycle shop. As you can see here, the difference in axle size between a common bicycle hub and the 14mm BMX hub is huge. When you are sourcing steering parts for the front of a Tadpole trike, you will basically need two of everything when it comes to the front wheels. As you can see in the completed StreetFox photos, the steering system is made using standard bicycle components, so you do not need any expensive machine shop work done. And the resulting steering system is much smoother than the traditional kingpin bolt-style steering system often found on go-karts. Your goal is to find two identical head tubes in the fork hardware to match. When I say identical, I am not referring to color or brand, but the overall length and width of the head tube so that both front wheels will be at the same height when the parts are installed. As shown in this photo, I have two identical head tubes and two matching fork stems that fit into the head tubes. These parts are cut from scrap bicycles. It doesn't matter if the head tube is from a 1960s beach cruiser and the forks are from a competition BMX bike, as long as the hardware fits together properly and the forks spin around without friction. I ended up using a 20-inch and a 26-inch fork, but again, this doesn't matter, as the fork legs are soon to be cut from the fork stem. As shown here, fork hardware consists of two bearing cups, a pair of bearings, and at least 2 locking nuts. Bearings are inserted into the cups balls first, and the fork stem should spin without friction of the bearings, and cups are the correct size. For more information on bicycle components or salvaging parts, check out the many tutorials posted on the chopzone.com forum. Before you start amputating the fork legs from the fork stem, first tap off the small bearing race installed just above the fork crown by tapping it with a small hammer. Tap all the way around the ring until it falls off so you can work on the fork legs without risk of damaging the bearing race with our hacksaw or angle grinder. How you cut the fork legs from the fork stem is up to you, but do try to avoid cutting into the fork stem when you are doing this job on both forks. I like to cut around the fork leg using a cut-off disc in my grinder, leaving about 1/4 inch as shown here. I then finish up the surface grinding with a rough grinder disc and then clean the area with a sanding disc. Keep the fork legs around for some other project. They make good headrest supports or seat frames. At this point, you have 2 perfectly clean fork stems like the pair shown here. The length of the crown area may not match on both fork stems, but this does not matter since we will be cutting them down to 1 inch to remove the excess crown area. A bit of tape around the crown area will make a good cutting guide, or you can draw a line around the crown using a marker. The cut line should be 1 inch from the top of the crown where the underside of the bearing race would have been sitting. Here are the 2 fork stems after cutting each crown down to 1 inch. The bearing races have been reinstalled by tapping them down the same way they were originally removed. Now both fork stems are exactly the same length and have the same amount of crown material. If you look closely at the bottom of the original fork crown piece that you have just cut, then you can see that it has a small bead of weld around its edge. This is because the crown is actually made of 2 pieces of tubing that fit together, one inside the other. You should run a small bead of weld around this area, as it was done on the original part you just removed, in order to secure the 2 pieces of tubing back together. The head tubes can now be cleaned up by grinding away the excess tubing left over from the original bicycle frame. As shown here, a little work with a grinder disc and flap disc will bring the metal tubing back to its original, ready to the weld state. Again, avoid cutting into the head tube metal when cleaning up the area, and take this opportunity to weld up any holes that have been drilled into the head tube where the other tubing was welded. A few passes around the outside of the hole will fill it with weld metal, so you can grind the area flush. Now you can clean all the fork hardware and reassemble the parts as shown here. Notice the small bead of weld on the underside of the fork crown where the cut has been made. Now you have 2 identical parts to make your lightweight and friction-free steering system. This steering kingpin system is far superior to the bolt and bushing system, which often has unacceptable play and friction. The bicycle head tube was designed to steer a bicycle wheel in a friction-free manner, so it only makes sense to use it to do this job on your trike. The 14mm axles will be held to the head tubes by a pair of axle mounting tabs. Originally, I had made a pair of machine tubes to do the same job, but that increased the cost of building the trike, and my goal was to keep the cost down and not use machine parts. So I came up with this system, which I think is easier to work with. Your goal is to make 2 1.75 inch by 1.25 inch tabs with a thickness of 1/2 inch so you can secure the axle to the fork crown. Since 1/2 inch thick plate is hard to come by and not easy to cut, I decided to make my axle mounting tabs by welding 2 1/4 inch parts together to form the required 1/2 inch total thickness. You can use any scrap metal, plate, or flat bar to make these tabs, as long as the required dimensions and thickness are met. This diagram shows the size and thickness of the axle mounting tabs, as well as the drilling for the 14mm axle hole, which is placed 3/8 inches from the end of the tab. A 14mm drill is not very common, so rather than try to find one, just use a 9/16 drill bit for the 14mm hole. 14mm equals 0.551 inches, and 9/16 is 0.563 inches, so the resulting hole will be perfect for the 14mm axle. If by chance you have a bit of scrap 7/16 inch thick plate, you can make the axle mounting tabs from that, but do not make them any less thick than 7/16 inch. Since I made my axle mounting tabs from 1/4 inch plate, I had to weld two pieces together in order to achieve the required 1/2 inch thick result. As shown here, the axle mounting tab on the left has been welded and ground clean and has a pilot hole drilled for the axle hole. The axle mounting tab in the right of the photo is fresh from the vise and has yet to be ground. But you can see that it is nothing more than two bits of 1/4 inch scrap plate welded together to form a 1/2 inch part. To drill the 9/16 axle mounting holes, start by drilling a small pilot hole using a 1/8 drill bit and then gradually work your way up to the 9/16 bit. I work my way up the drill bit set, skipping every third bit, so the final hole is the correct size. If you try to go straight for the big drill bit, your holes will probably not be in the same place on each axle mounting tab, or you will jam the bit and end up with the part flying out of the vise. I only own a hand drill, so a drill press is not required, although it would certainly make the job easier. With a 9/16 inch hole drilled in the axle mounting tab, it should fit snugly over the 14mm axle with just enough play to not have to force it on. The tab and the axle should form a 90-degree angle, and there should be plenty of axle length to get the axle nut installed as shown here. Another advantage of the axle mounting tab system over the hollow tube mounting method I previously used is that the axle does not need to be taken out and moved to one side of the hub. The other side of the axle can be cut flush with the locking nut as shown in this photo. There is no point having the axle sticking out past the outer side of each front wheel, as this would be a hazard to pedestrians in a close encounter, and also very annoying while trying to move your trike through a narrow doorway. Just use a hacksaw or zip disc and cut the axle flush with the lock nut. Now would be a good time to make sure that all of the axle nuts are tightly secured as well. There are a few angles that you need to get right when it comes Tadpole trike steering, so take your time and fully understand the next few steps before doing any welding. Nothing here is rocket science, so if you take your time and fix any obvious errors, the trike will handle like a dream. Shown here is one of the axle mounting tabs tack welded to the base of the fork crown at some slight angle. This angle is no mistake, as it creates what is called Centerpoint steering, so that the wheels turn directly on their axis when touching the road. This concept is shown in the next photo, with the line that travels down the fork stem directly to the center of the tire as it hits the road. Without this centerpoint geometry, the vehicle would swing from side to side as you turn the front wheels, causing a dangerous inertia at high speed that could launch you from your seat. Only extremely slow-moving vehicles can operate without centerpoint steering, and you will certainly need it for a high-speed trike like this. With centerpoint steering, the tire will pivot directly on its center, so there is no tire scrub or side-to-side inertia when making turns at high speed. Shown here is an imaginary line drawn through the center of the head tube directly to the road under the center of the tire, which is how the angle of the axle mounting tabs need to be calculated. This photo shows how I derived my axle mounting tab angle. By using a wheel with a fully inflated tire, I initially held the fork stem in place and made a mental image of the required angle. The axle mounting tab was then removed from the front wheel, and I tack welded it to the fork stem using my best guess from the image I had in my mind. Chances are you will get pretty close on your first attempt, but this needs to be checked by bolting the wheel back on the axle mounting tab and then inspecting the angle by drawing that imaginary line through the fork stem to the point of contact under the tire. You can also hold the wheel at 90 degrees to the ground and try turning the fork stem to see if the wheel actually pivots on its center axis. With a single tack weld holding the axle mounting tab to the fork crown, you can easily force the part into another position if necessary, but don't be afraid to break the tack weld and try again if your center point angle is obviously wrong. I did the tack weld 3 times to get to the angle shown here. You only have to do this guesswork once, as the other side can be made by copying the angle you get on the first side. As you can see, specifying an actual angle here would be useless, as it totally depends on your tire size, hub width, and even the type of hardware on your axles. Here are the 2 axle mounting tabs securely welded to the fork crowns after fully welding the sides of the joint. I copied the angle from one part to the next, so I would not have to go through all that guesswork again. When placed side by side, the fork stems and axle mounting tabs should look identical. At this point, you can weld the face of the joint, making sure you do both parts in the same sequence. By welding the joint using the same sequence, you ensure that both front wheels have the same angle. This photo shows the completed welding all the way around the axle mounting tabs on both parts. Since I use the same amperage setting and sequence to weld both parts, any slight distortions in the axle mounting tab angles have affected each part the same amount. A final test shows that my Centerpoint steering angles are almost perfect. 2 small holes have also been drilled in the axle mounting plates to lighten them up a bit. Of course, losing a few ounces of weight to drill shavings is not really important, but the parts do look more professional like this. Now that you have 2 identical wheels mounted to identical steering tubes as shown here, much of the hard work is now done. Eventually, you will need to mount each head tube to the cross boom at the correct angle. But other than that, the rest of the frame is pretty basic, and we will be working on the easy stuff for a while now. The only part of the bicycle frame that you need besides the rear swing arm is the small tube that carries the plastic plugs, allowing the swing arm to pivot up and down. Not all suspension frames are the same, but you can easily figure out which parts you will need even if they do not look like the ones shown here. Basically, you will be taking any parts needed to refasten the swing arm to the trike frame, so cut them from the original mountain bike frame. The entire StreetFox frame is made from 1.5-inch mild steel square tubing with a 1/16-inch wall thickness. This tubing can be ordered from most steel suppliers and is very easy to cut and weld. Steel suppliers like to rate tubing wall thickness using a gauge number, so 1/16 wall tubing will be called 16-gauge tubing. And although there is a slight difference between the two, your best bet is to tell them you want a length of 1.5-inch square tubing with a wall thickness as close to 1/16 inch as you can get. If you are a heavy rider, over 250 pounds, then you should ask for the next size after that, which will likely be 14-gauge tubing. Round tubing should be avoided for this project, as it will yield a very flexible frame, which will most likely be out of alignment after all the welding is completed. The main boom runs from the pivot point of the rear swing arm all the way to the front of the trike. The main boom also carries the seat rear support, the 2 cross boom tubes, and also allows the sliding bottom bracket to adjust for just about any leg length. The overall length of the main boom is determined by the size of the tallest rider that will use the StreetFox. To start, cut a 6-foot length of the square tubing to become your main boom. Yes, 6 feet is more than you will ever need, and you will be cutting it down once the bottom bracket has been set up for your tallest rider. It's better to start with an extra long main boom than end up an inch too short because you forgot to add the extra few inches added by the seat padding or something similar. The suspension, swing arm, pivot tube that was cut form the mountain bike frame needs to be connected to the end of your main boom, so you will have to cut the appropriate fish mouth shape at one end of the tube as shown here. A good way to do this is to use the pivot tube as a guide to mark the area to be ground. This way you don't take out too much material. The goal here is to make a good joint that will have no gaps once the part is welded in place. Again, your swing arm parts may differ, but the idea is the same. Before welding, tap out the swing arm bearings, as they are most likely just plastic plugs and would melt instantly during the welding process. This photo shows the swing arm pivot tube tack welded to the main boom on all 4 corners. Once you have the part tack welded and it has been checked for alignment, you can continue welding the joint starting with the top and bottom and then the sides. To ensure that the tube is welded in line with the boom, place a straight edge across one end of the pivot tube and check it against the length of the boom. The entire joint should be welded as shown here. Once the parts have cooled, you can tap the plastic bearings back into the pivot tube and then bolt the rear suspension triangle onto the main boom. The pivot tube may have been warped slightly due to heat distortion, so it may take a bit of effort to get the bearings to fit back into the tube. If distortion is extreme, you may need to work the tube back into shape using a large hammer. The rear triangle is bolted onto the pivot tube, completing a large chunk of the building process. As shown in this photo, the installed rear triangle can pivot up and down freely, and it should be in line with the rest of the boom when viewed along the length of the main boom. Currently, there is nothing to connect the suspension spring to, so we will work on that part next. The seat tube is a 14-inch long piece of 1.5-inch square tubing that will serve the function of connecting the suspension spring as well as becoming a support for the rear of your seat. This tube is cut to a total length of 14 inches, and then one end is cut off at 45 degrees as shown here. 45 degrees is a comfortable seat angle, but if you have other plans and understand how this angle will affect the rest of the frame, then feel free to alter the seat angle to suit your needs. A more upright position will place your head up higher, but could become uncomfortable if increased too much, making it difficult to pedal or even reach the handlebars. On the other extreme, a much laid-back seat will make the trike feel more like a low racer, making it difficult to see properly in traffic or even over your own feet. The top of the seat tube is cut off at 90 degrees and needs to be capped off to keep out moisture and anything else that may want to crawl inside. It is a rule of mine to never leave an open-ended tube, as this looks totally unprofessional, allows moisture into the frame, and could be a hazard due to the sharp edges of the tube. A simple cap can be made by cutting out a 1.5-inch square section of some scrap tubing, as shown here. The cap is simply welded along the seams using only enough heat to fill the joint with weld metal. After welding the cap to the open end of the tube, use a flap disc or sanding disc to clean up the joint so the tube will look like it never had an open end. These little details add up to take your final product out of the home-built zone into the professional-looking zone. It feels much better to be asked, how much did that cool trike cost, rather than how long did it take to build that? The seat tube is placed on the main boom in a position that will allow the suspension to travel properly when the main boom is placed at the required height from the ground. I could just tell you to measure 9.5 inches from the rear end of the main boom and mark a line, but depending on the overall shape of your rear triangle and the length of your suspension spring, the measurement that I used may not work properly for you. Of course, like all of my plans, I like to derive component critical measurements by using the set it up and check method, which ensures that your final design works out regardless of small differences in your donor parts. There are two conditions that need to be satisfied here, and to ensure that you get the correct placement of the seat tube. You will also need to install the proper rear wheel with a fully inflated tire and have the suspension spring you plan to use installed on the rear triangle. The first requirement is the clearance from the underside of the rear boom to the ground, which should be 9 inches. For this, I simply found a bucket that was 9 inches tall and placed it under the main boom as shown here. With the boom supported and rear triangle populated with the wheel and suspension spring, it is easy to see where the suspension spring needs to connect to allow at least 2 inches of spring travel, which is requirement number 2. If you place the seat tube way ahead of the rear triangle and try to connect the suspension spring to the very top of the seat tube, you will have added an extra 6 to 8 inches of unnecessary length to the frame. Sure, this would indeed work and might be a good way to add some battery or luggage space, but unless that is your goal, the seat tube should be placed as far back as possible, putting the suspension spring mount lower on the seat tube. As shown here, I have the seat tube held to the main boom with tape as I try to find the optimal mounting position, which was about 9.5 inches from the center of the pivot tube to the rear edge of the seat tube. If I lifted the rear wheel off the ground 2 inches, the top of the triangle had about ½ an inch of clearance before it would strike the top of the seat tube. So this was just fine for my suspension spring, which had only 1.75 inches of total travel. When you find the magic place, just mark that position on the main boom so you can weld the seat tube in place. This photo shows the seat tube tack welded to the optimal place on the main boom. A small tack weld is first placed in the center of the joint so you can ensure that the seat tube is in line with the rest of the main boom. View the two parts from all angles and manipulate the seat tube if an alignment adjustment seems necessary. When welding square tubing, order of welding can make a huge difference in the amount of heat distortion that will form as the weld metal cools. On the seat tube joint shown here, the alignment is more critical from side to side as it is on the top of the boom where the seat tube makes the 45-degree angle with the main boom. So the top joints on the main boom were welded first, followed by the 2 joints on each side of the boom. The first 2 welds basically lock the joint from any further distortion, or at least minimize it. The 2 front wheels are held to the main boom by 2 tubes I call the front arm tubes. On some trikes, these two tubes are a single length, which would be called a cross boom, but to ensure that shorter riders can enjoy the StreetFox without having their ankles rubbing on the frame, I decided to go with two tubes placed on an angle to give shorter riders a lot more footroom. Again, measurements may change slightly depending on the width of your front hubs, length of your head tubes, and type of hub hardware. So make all cuts a little longer than needed and work backwards, using your parts as a guide. Start by cutting the two front arm tubes to a length of 16 inches as shown in the next diagram. As shown in this diagram, the two front arm tubes are 16 inches in length, with a 22.5-degree angle cut off one end of each tube. 22.5 degrees is half of 45 degrees, so if you fold a piece of paper diagonally twice, you will have a handy guide to check the 22.5-degree angle. The two front arm tubes are welded together at the angle cut ends, so they form a total angle of 135 degrees when welded together. An angle checker verifies that I am very close to the desired 135 degrees. Welding is done on the front and rear of the joint, and then on only the top of the joint, leaving the bottom of the joint untouched so it can sit against the main boom tube perfectly flat. If you were to weld all the way around the two arm tubes, alignment of the main boom tube would be difficult since the weld would create a high spot. As you will soon see, the side of the joint that sits on the main boom tube does not need welding, as it will be secured by the welding between the rest of the front arm and main boom joints. This photo shows the side of the newly joined front arm pair that was left unwelded so it can sit flat against the main boom tube. If the welding at the ends of the other joints has created a high spot on this side of the joint, grind off any of the excess welding bead until you can place a flat object directly over the joint so it sits perfectly flat. The top side of the front arm tubes is fully welded as shown here. Since the front arms are now joined to create one single piece, I will now refer to them simply as the front arm boom. Whenever a non-critical weld is clearly visible, I try to grind the weld metal flush with the original tubing for aesthetic purposes. You might think that the weld holding the two arm tubes together is one of the most strength-critical welds on the entire frame. But as you will soon see, the joint between the main boom and the unwelded side of the front arm boom is what really holds the front arm boom to the main boom, so you can easily afford to clean up the top weld. While cleaning up welds, be careful never to dig into the weld material, creating a valley in the joint. A little hill over the joint is much better than a little valley, which could seriously compromise the strength of the joint. Now that you have the two front arm tubes joined together, forming the front boom, you must trim them down to achieve the desired track width, since the initial measurement given was longer than you need. Because track width is measured across the fully inflated tire centers, you will need to have your front wheels installed on the head tubes with fully inflated tires and all the head tube hardware installed. As shown here, you need to know the distance from the center of the head tube to the center of the tire, or rim, in order to determine how much material needs to be trimmed off of the front arm boom in order to end up with the desired track width. Again, 30 inches is a good track width to shoot for unless you have other requirements. It may be difficult to measure the distance from the center of the head tube to the rim center with high accuracy, so just try to get a decent estimate within a quarter inch or so. My measurement was 2 inches, but yours may differ slightly. Once you have determined how far it is from the head tube center to the rim center, you can use that measurement to figure out how much length needs to be cut from the arm boom to get the desired track width. We took the measurement from the center of the head tube, since this is approximately where it will end up once you cut the fish mouth out of the arm boom to weld it in place. Now run a measuring tape across the arm boom assembly from center to center as shown here, so you know what the track would be right now if the arm boom was left uncut. The distance across my arm boom assembly from center to center is currently 28.5 inches. So if I add the extra width given by the two head tubes, which is 2 inches times 2 to equal 4 inches, I would end up with a 32.5-inch track. Obviously, I will need to chop off 1.25 inches from each arm on the arm boom assembly to end up with the desired 30-inch track. Therefore, the distance across my arm boom assembly needs to measure exactly 26 inches after trimming. Here is a close-up of how the arm boom is to be measured across its width. A small mark indicating the center of the tube is drawn, and this is where the measurement is taken at each end of the arm boom assembly. After a little calculating magic, I have determined that the overall width from point to point on my front arm boom assembly needs to be reduced by 2.5 inches. So I have marked a 1.25-inch cut line at the end of each arm as shown here. The resulting center-to-center distance of my arm boom will soon be 26 inches, which will create a trike with a 30-inch track width by adding the distance from each head tube to the wheel center, 4 inches total. The head tubes are welded to the ends of the front arm boom at such an angle that the tires end up at 90 degrees to the ground. Since we are using Centerpoint steering, the head tube angle is not the same as the axle or the wheel, so this needs to be taken into account when cutting the fish mouth joint on each end of the front arm boom. For now, simply trace a line using a head tube, or something of equal diameter, on the top of the front arm boom assembly as shown here. The top of the arm boom is the side with the weld, opposite of the non-welded side. The front arm boom will mate with the top of the main boom at a distance of 12 inches as measured from the point of contact to the 45-degree corner formed between the seat boom and main boom. This distance allows plenty of room to mount your seat base and places the handlebars in an easy-to-reach comfortable position. This photo shows the first tack weld made at a distance of 12 inches from the seat corner as described. A single tack weld is made so the angle can be checked and easily adjusted if needed in order to get the two arms at the same angle in relationship to the main boom tube. An adjustable square angle finder is used to compare each side, making slight adjustments until they are both equal. At that point, you can place another tack weld on the front of the joint to lock down the angle. Here you can see the front arm boom tack welded in two placed along the top to lock it in position after the angles on each side have been checked to be equal. Notice there is plenty of room, 12 inches, for your seat base, so you can use very thick seat padding if you like. A mesh seat with a frame could also be installed as there is plenty of room. Also notice that the arm boom S welded on the top side of the main boom, which will help keep your chain line and steering system simple and clean. With the angles between each arm and the main boom equal, complete the joint by welding the two top sides first. You will want to use a clamp or vise to hold the boom securely to the frame to avoid any side-to-side distortion caused by welding heat. This photo shows the completed welds on the front and back side of the arm boom and main boom. Once the top of the arm boom and main boom joint is welded, you can finish up on the underside of the joint. Use the smallest bead of weld you can in order to keep heat distortion to a minimum, and make sure you weld both sides using equal amperage and travel speed so any deflection is equal on both sides. The next step is by far the most complicated part of the entire build, and will most likely require more than one try to get right. The good news, after this, you are home free, as the rest of the build is going to feel like smooth sailing. Head tube angle is what you need to calculate now, and it is by far the most difficult part of a Tadpole trike build. You have to get the head tube angles correct in two ways. First the center point angle, and then the caster angle. You also have to do this twice, making sure everything is mirrored on both sides. As shown in this diagram, you have to get the head tubes on such an angle that the wheels are standing at a 90-degree angle to the ground, and the head tubes are angled slightly forward, creating the desired 75-degree caster angle. The 75-degree caster angle allows the wheels to self-center, creating a more stable ride at high speed with a good degree of response. If you relax the caster angle too much, your wheels will tend to flop from side to side, and you will increase your turning circle by reducing the amount of steer. If you make the head tube angle too steep, then your steering will be instantly responsive and somewhat twitchy, especially at higher speeds, where you will tend to wobble back and forth as you pedal hard. 75 degrees seems to be a good angle for a trike of this wheelbase, but feel free to alter this angle if you feel that you know what you are doing and how it will change the handling characteristics. The alignment of each head tube will be determined by the shape of the fish mouth cut at each end of the front boom arm, which is why the top cutout was made earlier as a starting point to work from. You should take a small amount of metal out a bit at a time and check U angles often in order to avoid taking out too much material all at once. The odd-looking fish mouth cut shown here is what I ended up with after spending an hour or two with a small grinding disc and a round hand file. There is no magic formula or easy method I know of to get these angles in a hurry, so be prepared to spend some quality time with old-fashioned hand tools. Patience is the only way to win this battle. Using the bucket trick, I raised the front boom up to the correct height so I could check my work each time I took a little metal out of either of the fish mouth cuts. The front arm boom should meet each head tube as low as possible, leaving about ½ inch of head tube material sticking out past the underside of the boom arm so you can weld the joint without melting the edge of the head tube. This height is not critical since it is really determined by the height of the head tubes, but on my trike, this height was approximately 11 inches from the ground, slightly ahead of the boom joint where my bucket is placed as shown here. The process of grinding a little, then checking angles takes a while, but if this was easy, then everyone would have a cool custom trike, and the results of your hard labor would then be worth a lot less. If you want to keep the head tubes locked on the fork stem, you can add some tape around the bearing cups, or simply remove the top bearings, which will keep the head tube from rolling all over the place when you are using the wheels as a guide as I am. No welding is done until both wheels pass visual alignment inspection from every possible angle. After your grinding, filing, and inspecting ordeal is over, it is time to weld the head tubes to the arm booms so you can get on to the easy stuff, like riding your trike. Again, I cannot offer any magical solutions that will ensure an instantly aligned head tube pair with minimal effort, so be prepared to fiddle, break tack welds, and try your patience. I prefer to place the frame up high enough so I can stand back and compare the wheels to the ground and the wheels to each other. Here you can see the main boom held securely and parallel to the ground using a workbench vise. At this point, I have also placed one small tack weld on each head tube in hopes that my fish mouth cuts were close enough that I could force each head tube into alignment and continue welding. I was lucky with the left side, but the right side was visually out of alignment enough that I decided to do a little more filing to correct the error. This is one stage in the build where correcting your errors will make a huge difference to the look and feel of the finished product. I normally do not weld a frame with my good wheels or bearings installed, but this is one time where it is impossible to do otherwise, as you really need those wheels up on the bench for close visual inspection. An old towel or cloth placed over the tire and rim will keep welding spatter off of the wheel. Also, always place your ground clamp on the frame, not the head tube hardware, or current will surge through the bearings and destroy them, or the cups they are installed in. With a single tack weld on the head tube, you should be able to manipulate the head tube enough to get the wheel aligned the way it needs to be, with a focus on the wheel being at 90 degrees to the ground. When the wheel is where it should be, another tack weld on the other side of the joint should hold that head tube securely enough to later remove the fork hardware once both sides are looking good. Remember, this alignment counts, so break a tack weld and file away if you need to. With both head tubes securely tack welded in place, perform one last vigorous alignment quality check because the next step is the point of no return. I placed the frame and wheels back on the ground and then put both wheels in the straight ahead position so I could check their 90-degree alignment directly from the front as shown here. If both wheels seem to be standing at a perfect 90 degrees to the ground, then there is a good chance that both your head tube caster angles are also close to the desired result and equal as well. Look through the spokes at both head tubes to see if they are both at the same angle, and a very slight difference is not nearly as bad as a wheel not being at 90 degrees to the ground. Fix any errors before final welding. Welding the head tubes in place is done like any other welding, starting along the top of the joint, then the bottom, and finally the sides. Weld both parts using the same sequence, so any distortion is copied to both parts equally, and make sure there are no holes or gaps in the weld. It is a good idea to tap in an old head tube cup on the lower side of the head tube when you are welding, as this will help keep the head tube from becoming oval from heat distortion. Here is the almost completed StreetFox frame after an epic adventure with multiple and duplicate angle cutting and welding. If you enjoy bicycle building as a hobby, then every minute was pure fun. But you can sure learn to appreciate the high price tag on a Tadpole trike when you consider how much effort it takes to get here. Once your suspension spring is mounted to the frame, you will be able to place all three wheels on the trike and roll it around your garage, a great milestone in any bike build. The suspension spring is held to the rear of the seat tube using a pair of 1/8 inch bits of flat bar, or you could simply slice them out of your donor mountain bike frame like I did. As shown here, the suspension mounting tabs can be cut from the donor frame, bypassing the need to drill the appropriate holes for the mounting bolt. The suspension mounting tabs are shown installed in this photo, salvaged from what was left of the original mountain bicycle frame. If you decide to use flat bar to make the tabs, then just make sure you make them both the same size and drill the appropriate hole in each for the suspension spring bolt. Since you have already figured out where your suspension spring needs to be mounted, it's just a matter of installing the tabs on the suspension spring, then using it as a guide to make the first few tack welds. The spring can then be removed and the tabs completely welded to the rear of the seat tube like this. I would recommend that you install the front wheels and fork hardware, and then get out that 9-inch tall bucket to prop up the rear of the frame, just so you can ensure that your ground clearance is exactly what it should be. Braking on a Tadpole trike is another puzzle that is a little more complex than that of a Delta trike. Personally, I would be just fine with trusting one good rear brake, and often I will leave it at that and allow the builder to decide if they want to install standard caliper brakes on the front of a bike. Of course, standard front brakes are simply not an option on this trike, since there is no place to mount them, so this will be addressed. Some Tadpole trikes have hard-to-find custom drum brake hubs or disc brake hubs with custom axles, but the goal here is to avoid all expensive or non-standard parts, so I will avoid those two options. Another puzzle is what to do with 3 brakes and 2 levers, but there are always answers. To get a brake on each front wheel, you will need to make a brake support arm that allows you to place a standard bicycle brake in the appropriate place around the wheel. To do this, a pair of L-shaped brake support arms will be made from some 3/4 inch square tubing with a 1/16 inch wall thickness. These tubes are shown here and have been cut as per the next diagram. The brake support arms need to wrap around the inside of each front wheel to allow the installation of a standard caliper type bicycle brake. Because of the tight 1/2 inch clearance between the brake support arms and the tire, you should look ahead in this plan and consider the type and size of tires you have chosen for your trike. The measurements given here are based on a 2-inch wide 20-inch tire with minimal tread, which is a common choice of tire for this project. Your dimensions may need to be adjusted. The 2 brake support arms are shown here. After tack welding them together for a test fitting, the brake arms will connect to the fork crown and should come around the tire so that there is 1/2 inch between the widest part of the tire sidewall, as well as between the top of the tire and the small 90-degree portion of the brake support arm. Basically, you are making a half fork to emulate the way a caliper brake would hug the tire on a typical front fork. If you are satisfied with the position of the brake support arm in relationship to your front tire, then completely weld around all of the joints and then cap off the open ends of the tubing as it was done for the seat tube. Avoid weakening the joint by grinding away too much weld metal if you decide to clean the welds flush with the base metal like I have. The brake support arms are connected directly to the fork crown at a 90-degree angle as shown in this photo. Ensure that the clearances between the arm tubing and the tire are not less than 1/2 inch, so a few scraps of 1/2 plywood in between the tubing and the inflated tire can be used to help while you are tack welding the parts together. The brake support arms are only tack welded in one spot at this point, so they can be aligned properly with the wheel. Here you can see how the brake support arm should look when viewed from the top of the wheel. Notice that the arm comes from the fork stem at a bit of an angle as it heads towards the outer edge of the tire. The result is 1/2 inch of clearance between the top and sidewall of the tire and the brake arm tubing. This photo shows the brake support arm as viewed from the end. Notice the small tube is at 90 degrees to the tire rather than the fork stem to which it connects. This is necessary as the brake also needs to be mounted at 90 degrees to the wheel, so the brake pads hit the edge of the rim squarely. The brake support arms can be completely welded to the fork stem crown once you have checked the alignment with the tire. Welding should be solid and gap-free, as the brake arms will be put under considerable stress during a fast stop from high speeds. The same process must be done to both brake arm support tubes, making sure alignment with the wheel and rim is correct for proper braking contact. Here are the two completed parts ready for installation. At this point, you can roll your trike forward, and the two front wheels will fall into line and automatically track together due to the caster angle of the head tubes. Of course, you can't expect this to be safe on the road, and if you try to move the trike in reverse, the two wheels will point together and instantly lock up the vehicle. Like any vehicle with dual front steered wheels, the two wheels must be made to turn together, taking into account that the wheel on the inside of a corner must actually turn sharper than the wheel on the outside. This might sound like a complex problem, but is actually a very simple problem to solve. The name for this type of steering is Ackermann steering, and you can learn a lot about how it works by hitting your favorite search engine for more information. The good news is that I have figured out all of the proper steering geometry, so you will not have to, although knowing how and why it actually works is always a good thing. The two front wheels will turn together because they are joined by a pair of steering control arms, a pair of spherical rod ends ball joints, and a control rod. The position of the control arms in relationship to the pivot point of the fork stem actually determines how much one wheel increases its angle on the inside of a corner. So we can say that Ackermann steering is just a factor of control arm placement. If you have too much Ackermann effect, then the inside wheel will start to scrub or completely lock up as it flops all the way against the frame. If you have too little Ackermann angle or none at all, then one of the wheels will have to scrub around every corner, causing you to slow down and wear out your front tires in a hurry. This photo shows the two control arms, which are nothing more than 2-inch long pieces of 1-inch wide flat bar with a thickness of 1/8 to 3/16 inches. The holes are drilled approximately 1/2 inch from the ends and are the size needed to connect the ball joints that you decide to use. Ball joints with a 3/8 inch hole diameter are a good choice. Mark a point on the underside of the brake support arm 5 inches from the welded joint as shown here. This location is where you will install the control arms for proper Ackermann steering compensation. The X marked on the far side of this line indicates that the control arm is on that side of the line, not on the center of the line. To determine this control arm location, I spent the day trying random places along the brake support tube using many different length control arms until I could make every possible turning circle with little or no tire scrub. This took at least 20 attempts, but now saves you from having to do the same. This photo shows the two control arms welded to the brake support tubes, so the distance between the edge of the control arm and the fork stem is 5 inches. The 3/8 inch holes drilled in the control arms match the ball joints I found at the local hardware store. Ball joints are actually called spherical rod ends, so remember that if you are asking for them at a bearing store, as they like to use the proper terminology, most of us just call them ball joints, so I will continue to do so from now on. The two ball joints and the control rod are shown in here. My ball joints have a bolt on the body and require a bolt to hold them through the ball holes, while some may be the opposite, including the bolt on the ball part instead. It really is not important which type you choose, as long as the bolt or bolt hole is no smaller than 3/8, and the ball or bearing is not made of plastic. The control rod is just a 1/2 inch hollow tube from the hardware store with a 1/16 inch wall thickness. The 3/8 bolt just fits into the tube, so this allows a nut to be welded at each end of the tube to make the steering alignment adjustable. This photo shows how the 3/8 bolt on the ball joint body fits right into the hollow control rod, using a nut to allow the ball joint to be adjusted about 1/2 inch up or down. This nut will be welded directly to the end of the control rod, and then another nut will be used to lock down the ball joint once the two front wheels have been perfectly aligned. The length of the control rod is determined by installing all of the front wheel hardware and the rear wheel, then walking the trike forward until both front wheels have tracked together for at least a 4-foot distance. At this point, try not to disturb the front wheels as you measure the exact distance from the center of each hole on the control arms that you just welded in place. You can then subtract whatever length is needed from this measurement so that the ball joint holes will be the same distance apart as the holes in the control arms. The ball joints should be set up so they can be screwed in or out the same amount allowing optimal tire alignment, fine-tuning in each direction. Here is what the completed control rod should look like once the nuts have been welded at each end of the tube and the ball joints screwed in and locked down. At this point, the center-to-center distance between ball joint holes is exactly the same as the center-to-center distance between the control arm holes after rolling the trike forward. I did not even have to do any fine-tuning of the steering alignment after this point, as the steering was tracking perfectly and friction-free after assembling the trike for the very first time. In this photo, you can see the control rod installed by putting a bolt through the ball joints and the two control arms. I would recommend you use good quality bolts with locking nuts for all steering hardware, so that the nuts don't work their way loose over time due to vibration. If you lose the control rod at high speed, one wheel may flop to the side and cause the vehicle to roll or steer wildly out of control. Don't take chances with low-quality parts on steering or braking components. The ball joints are placed on the top of the control arm as shown here, so they are easy to inspect if required. You could certainly place them on the other side of the control arm, but then they are always hidden from your view. Once the steering system is ready for testing, the trike should roll in a straight line without any resistance and steer around most sharp corners without any tire scrub. Obviously, steering too far in one direction will cause the inner wheel to travel past the steering center and literally flop all the way over. But in normal steering conditions, this will never happen. If you move the wheels from side to side, you can really see how the Ackerman steering affects the inside wheel, casing it to steer at a tighter angle the farther you move the outer wheel. If your trike seems to roll with any friction or obvious tire scrubbing, then you will have to unbolt one of the ball joints and adjust it properly. Remember, rolling the trike forward and allowing the two front wheels to self-center is a good way to find the perfect alignment point. It would be very difficult to guess the exact placement of the bottom bracket for your inseam, leg length, without making a small error. A fixed bottom bracket also means that you could never alter the seat or adjust the StreetFox for anyone but yourself, so an adjustable bottom bracket is the only option. If you cut the bottom bracket from an old bicycle frame and leave a 12-inch or longer section of the seat tube connected for the front derailleur, you can create a very functional adjustable bottom bracket with nothing more than a pair of steel plates. The bottom bracket and included seat tube will be mounted to the main boom with a clamp arrangement that allows the assembly to be placed practically anywhere on the boom to allow riders of varying heights to ride the bike. The two plates shown here along with the bottom bracket and seat tube stub will form the sides of the clamp that will hold the bottom bracket against the side walls of the main boom as they are forced together by two bolts. The bottom bracket and front derailleur tube move together along the main boom, so you do not need to worry about the position of the derailleur over the chainring. The chain is cut to the perfect length once the bottom bracket has been adjusted for the main rider, but will still allow a few inches of adjustment in either direction without a chain alteration due to the spring-loaded rear derailleur. Of course, the difference between a 6-foot 5-inch versus a 4-foot tall person will likely require some chain adjustment, but this can be done in less than a minute with an inexpensive chain link tool. Cut two 3/16-inch thick pieces of plate or sheet to make the shapes as shown in this diagram. The round area is cut to conform to whatever size bottom bracket you decided to go with, and the two bolt holes will be drilled for 3/8-inch bolts. The bolt holes are drilled at the edge of the plates so that there is 1/8 inch of material between the hole and edge of the plate. These two plates will form a vise that will clamp the bottom bracket to whatever position on the main boom you want. Trace around the bottom bracket shell to draw a line on the plates as shown in the last diagram. The marker line should meet the corners of the plate to ensure that you don't cut out too much off of the plate when grinding out the rounded area. If you take too much metal away from the plate, there will not be enough room between the bottom bracket and the clamping bolts for the main boom. When grinding out the trace circular area for the bottom bracket, as shown here, place both plates in the vise so they can be done at the same time. This will ensure that both plates are exactly the same size. Try to make the gap as small as possible around the bottom bracket shell so that there is less distortion as the plates are welded. If the bottom bracket becomes overly distorted, it will be a serious challenge trying to screw the hardware back into the bottom brackets without stripping the threads. In order to get the two plates aligned with each other and at the correct spacing, a bit of frame tubing can be clamped between the two plates as shown in this photo. This will allow you to set the bottom bracket into the correct position for tack welding, as well as ensure that both plates are aligned with each other so the bolt passes easily through both holes. I also placed a sheet of paper, folded in half, between each plate and the side wall of the tubing in order to allow a little clearance between the clamp plates so that the unit is not so difficult to slide when making adjustments. Without the small gap, it is easy to scratch the paint if you plan to move the bottom bracket around a few times. As shown here, I used an adjustable square set to the required 56 degrees in order to set up the bottom bracket and derailleur tube to place two small tack welds at the top of the joint. It may be a bit tricky to get the first tack weld in place while holding the bottom bracket in position, but once this is done, the rest is easy. With the piece of frame tubing as a guide, you will automatically have the correct distance between the plates. Now you will need to ensure that there is approximately equal distance between each plate and the edges of the bottom bracket. In other words, the bottom bracket will be in the center of the main boom as viewed from above. Here you can see the first tack welds done at the top edge of the plates in order to secure the parts together. Ensure that the derailleur tube angle is close to 56 degrees and that the bottom bracket is at 90 degrees to the square tubing. You can also move the clamps to hold the plates in a position that will allow you to weld around the entire joint. Also, welding is only done on the outside of the joint, not between the plates. If the inside of the joint is welded, the weld bead will not allow the bottom bracket to sit directly on the frame tubing and could cause alignment problems. Because of the way the clamp system works, there would be no added benefit from welding the inside of the joint anyhow. The two plates will form a vise-like grip on the frame tubing when the 3/8-inch bolts are tightened. In order to drill the holes into the plate, draw a line that represents the bottom corner of the frame tubing as shown here. Now you can punch and drill the holes using the line as a guide that will allow you to ensure that the holes stay below the line. If the holes are not below the line, you will not be able to pass the bolt through both plates because it will hit the frame tubing instead. With the derailleur tubing cut to length, it is a good idea to cap off the open end of the tubing so that it looks better and keeps any moisture out. A washer is welded over the end of the tube and then completely filled in around the joint and the hole. To fill in the washer holes, several passes are made around the edge until completely covered in weld metal. After welding the washer in place and grinding the area clean, you can't even tell the tube once had an open end. Going the extra mile can make your final product look very professional. Here is the sliding bottom bracket secured to the frame. Notice that the bolts are fairly close to the underside of the frame tubing thanks to the guidelines used to drill the holes. The derailleur tube is very close to the 56-degree angle as well. Tighten the bolts enough so that you can't force the bottom bracket to move by pulling on the derailleur tube, but not too tight or you may actually crush the frame tubing. You are almost ready to cut the proper length of chain and connect your transmission system. The obvious problem right now is the fact that the chain will rub on the underside of the right front arm tube, so an idler pulley needs to be installed in order to guide the chain under the tubing. Almost all Tadpole trikes have at least one drive side idler pulley, and this is unavoidable due to the low seat height and position of the front chain ring. Fewer chain idlers and less of a bend in the chain is always better, since idlers and sharp chain bends cause extra friction in your driveline, robbing you of your top speed. The StreetFox has only a single idler, and it only bends the chain slightly, so the transmission is very efficient. This photo shows the V-belt idler pulley that is used to guide the chain. It is a commonly available 3-inch diameter, 1/2 V-belt idler pulley with a 3/8 ball bearing mounted in the center. The chain idler pulley is mounted to the right side of the main boom just behind the right front arm tube, as shown here. Hold the pulley against the frame so you can determine the best place to install the idler pulley bolt. When you are done, the pulley should be as close to the arm tube as possible without rubbing, and the pulley should stand off from the frame about 1 inch, which is why the lawnmower wheel shoulder bolt worked perfectly for this job. A bolt and a few nuts could also be used if you can't find a decent shoulder bolt like I did. Here you can see the chain idler pulley guiding the drive side of the chain around the right front arm tube at a very slight angle. At this point, you can install your front cranks, rear derailleur, and fiddle around with your chain tool until you get the chain cut to the correct length. A chain link tool can be purchased from any bicycle shop for about $20 and will save you countless bangs on the thumb if you try to break and connect a chain using a punch and hammer. You will probably need 2 full bicycle chains and possibly a small part of a third chain to make the trike chain. So try to ensure that all chain segments are the same size and type. Bicycle chains are not expensive, so it might be best to work with new materials here. There is a chain joining tutorial showing how to use a link tool on the chopzone.com forum. Seating is a personal choice, and since the StreetFox has such a simple frame, you can install just about any type of seat you would like, from a simple board seat to a high-tech adjustable mesh and frame style seat. I prefer the simple board and pad seat over mesh seating, so I will show you how to fashion a comfortable and simple seat using some plywood, foam, and fabric. To use a board-style seat, you will need to bolt it directly to the frame, but since drilling holes into the main boom is a bad idea, a few seat mounting tabs like the ones shown here need to be made. 4 lengths of 2-inch long, 1/16-inch thick flat bar have been cut and will be welded to the main boom to hold down the 2 plywood seat boards. The 2-piece plywood seat has a base and a back, which are bolted to the seat mounting tabs. The tabs have been welded to the main boom and seat tube as shown here. The tabs are flush with the top of the square tubing, and the welds are ground flush as well. You can now mount any type of plywood seat or even a fishing boat seat to the frame. Later, I will show you how I made my minimal yet comfortable wooden foam seat. The steering system is now complete, but you have no place to hang on, so the handlebars need to be created so you can get out and test ride your new trike. Handlebars are another piece of hardware that can be modified to suit your own style, so feel free to experiment with angle, size, and shape using the basic design shown here. No matter how you decide to fashion your handlebars, you will need 2 gooseneck stems that can fit into the fork stems installed on your trike. This photo shows the 2 standard steel bicycle goosenecks I have decided to cut up to make my handlebars. Do not worry about the condition of the gooseneck clamp, as this simple handlebar design only requires the stem. Trim the clamp and the neck away from both goosenecks, leaving nothing but 2 equal-length gooseneck stems and the mounting hardware as shown here. You can now find a set of bicycle handlebars to cut in half and weld directly to the gooseneck stems in order to create your handlebars. It may take some experimenting to find the most comfortable angle and length, but a good place to start is with a pair of these common granny bike handlebars. The handlebars need to be cut into 2 equal pieces to form a left and right handlebar for your trike. As here, the handlebars are cut in half, then ground out to mate with the gooseneck stems at a position that feels comfortable and allows a full range of motion and easy reach of the brake levers. Most likely, this optimal position will take some experimentation to get right, so it's a good idea to have your seat installed, or at least a few boards so you can sit on the trike and get a feel for where your hands feel most comfortable. With your seat or a few boards installed on the frame, test your handlebars by only tack welding them to the gooseneck stems at first, so that you can make sure you like the position and angle of the bars. I found that having my hands just slightly inside the edge of the front wheels at the position shown here seemed just right. When you do find that perfect handlebar position and angle, weld one of the handlebar halves with a few more solid tack welds and then install it back on the trike for one final test. If the handlebar seems good, fully weld the joint and then do the same to the other half, trying to make it exactly the same as the first. Remember, there is a right and left side, so you can simply mirror the fish mouth cut from one bar to the other. If you choose to make a simple wooden foam seat like I did, you may also want to make an adjustable backrest as well. This is of course optional, and you could simply choose to make your seat back a lot taller instead. The seat is most comfortable if it supports the upper part of your back, so that you do not have to hold your head forward while riding. Using some leftover mountain bike handlebar tubing and a pair of those knuckle protectors, I came up with a simple yet functional adjustable backrest system. I knew where the backrest needed to be placed by simply sitting on my seat. Then I cut the old mountain bicycle handlebar tubing to the correct length, then welded it a section of one of those knuckle protector clamps I had in my scrap pile. Here's the resulting assembly, which looks like some type of long gooseneck. The backrest will be made just like the rest of the seat, so a pair of seat mounting tabs are added to the backrest support tube, just like they were added to the main frame earlier. To allow the backrest to adjust for comfort, a small section of the handlebar tubing was welded to the top side of the seat boom tube, as shown here. Now the clamp can be tightened to hold the backrest tube at whatever angle feels best. Plastic handlebar plugs have been used to cap off the ends of the tubing, since they fit perfectly. Yes, you are almost ready for a test ride. You may have noticed that the return chain, non-drive side, is hanging pretty low to the ground and can easily flop around, bouncing off of the rear wheel. Sure, you can leave it like that, but there is nothing uglier than a flopping return chain to ruin the nice lines of your trike. A hanging return chain makes your vehicle look unfinished and will let dirt collect in the chain as flops close to the ground. To keep the chain under control, all you need is a small idler wheel made from just about any lightweight pulley, skateboard wheel, or even an old rear derailleur, like the one shown here. There is absolutely no stress or tension on the return chain, so you do not have to use a ball-bearing pulley or worry about the diameter. Even a bit of garden hose can do the trick. Here is what is left after removing most of the derailleur parts. A perfect idler system, ready to be welded directly to the main boom. The only goal here is to pick up the slack chain so it does not flop around or hit the ground when you are hitting the trails on our trike. By welding the derailleur part to the rear of the main boom, the problem of an ugly flopping chain has been solved. A bit of garden hose, skateboard wheel with a slot cut, or even another V-belt pulley would also do this job, so dig through your junk pile for ideas if you do not have an old derailleur to butcher. By drilling a hole in the brake support arms, you can simply drop in a pair of stand bicycle caliper brakes for your front wheels as shown here. The hole should be directly in line with the center of the tire, so both brake pads hit the rim at the same position. Now your trike has 3 brakes, which will require 3 cables. The problem is that you only have 2 hands and therefore will only have 2 brake levers. Obviously, one lever will have to pull both front brakes, and there are several solutions to this problem. One option is a ready-made cable that looks like one cable into a small housing with 2 cables coming out. Again, this is a common BMX part that most bicycle shops will know where to get. The best option, which is the one most used on Tadpole trikes, is a brake lever that is already set up to take 2 cables. You might have to search the internet for dual brake lever, but there are several companies that make them. I like a minimal seat on most of my vehicles, so the plywood, foam, and fabric system seems to be my first choice. You should really consider your seating wisely, as everyone has a different opinion of what is comfortable, and my system may not be the best for you. My seat is 10 inches wide, with a base length of 10 inches and a back height of 18 inches. The 2 parts shown here are shown being cut from some 3/8-inch thick plywood. The rounded front and top were drawn by tracing a dinner plate and a bucket lid. To join the seat base to the seat back, I cut out a pair of 3-inch long pieces of 1/16-inch thick angle iron and then hammered them out to the angle of the seat. Here are the 2 angle iron pieces with wood screw holes drilled into them. Seat foam material should be comfortable to sit on, but not so soft that it does nothing for you. Brown sponge foam is useless, and hard styrofoam is no better than bare wood. For my seat, I used some quality 1-inch thick seat foam for the back of the seat, and some scrap 2-inch thick packing material foam for the base. Both pieces of foam were glued to the wood using adhesive spray and then trimmed along the wood using the angle grinder. As shown here, the angle grinder makes nice work of trimming the edge of the foam around the edge of the wood. Be careful when grinding foam with your grinder though, as the foam ends to grab the disc if you try to take off too much at once, or don't hold the seat securely when doing the work. Seat padding is simply cut to fit, then stretched over the foam to be stapled on the back of the seat. A real seat is sewn together as a top cover with sides, but this simple upholstery system works equally as well and takes very little time. If you stretch the material as you add each staple, you can probably get most of the wrinkles out of the material. A thicker material will be more difficult to work with, but the results can be decent if you take your time. Use a lot of staples, keep the material stretched around the corners to reduce the wrinkles. After stretching and stapling, your material will likely be wrapped tightly around the seat to look like the seat shown here. To cover up the back of the seat, another piece of material can be cut to the shape of the seat back and then stapled around its edges. Plastic or very thin sheet metal can also be used to hide the ugly staples and bare wood. Because the seat was covered with one continuous piece of material, the seam at the center was not perfect, so I stretched a length of seatbelt material around the seam and stapled it to the wood. The backrest is made exactly like the rest of the seat and then covered with a piece of sheet metal to hide the wooden staples. I decided to use metal rather than more staples and material to finish up the backrest because it would be much more visible on the trike, so it should look professional. The last thing that needs to be done is the trimming of the excess main boom length. With your seat and cranks installed, have the tallest rider sit on the trike, wearing shoes, and set up the adjustable bottom bracket to the correct place on the main boom. Now mark the boom, leaving a few extra inches, and cut away any extra length that will not be necessary. If you plan to add a fairing or body later on, you may consider leaving the boom extra long. Of course, you have to cap off the open end of the boom tube just like you did with the seat tube, so it looks clean and finished. Waiting for paint and primer to dry is a painful experience, but don't lose patience and try to get your trike on the road before the paint or primer has cured. Often, primer needs a full day to dry, and paint will not be ready for handling for at least 2 days. I always use department store spray cans, and usually the results are very good. After 2 days of paint curing, I hit the garage and eagerly assembled the entire StreetFox in about 2 hours. All bearings were cleaned and greased, and new handle grips, tires, cables, and chain were installed. The completed bike shown here really looked like a factory job, and it handled as well as it looked. A cycle with 3 brakes, 2 levers, and 2 shifters has a lot of cable routing and planning that needs to be done. I really don't enjoy running cables all over the place, but this is a necessary job that has to be done. So take your time and plan ahead before cutting any cable to length or adding any zip ties. Avoid any sharp bends in any cable. Make sure the wheels can turn from side to side without putting a cable under great tension, and always replace any rusty, frayed, or stiff cables with new ones. Both derailleurs will need to be set up properly by adjusting the high and low limit screws so the chain does not travel past the largest or smallest chain ring when shifting. Adjust the limit screws before the cables are installed by simply moving the derailleurs by hand to set the minimum and maximum travel distances. This photo shows the front derailleur being set up before the cables are installed. The brakes need to be fine-tuned so that they don't rub when not in use, but at the same time grip the rim with optimal power when the lever is fully engaged. Each brake lever has an adjustment screw, and it should be screwed all the way in when you initially set up the brakes. If the brakes don't grab hard enough, slowly turn the lever adjustment screw counterclockwise to stiffen up the brakes. A tiny bit of brake rubbing is okay as long as you can spin the wheel freely. Setting up the front brakes is done in the same way as it was done for the rear brake. There is an adjustment screw on the actual brake body, just like the one on the brake lever, so both should be screwed fully clockwise when first setting up the cables. Go over all of the cables one last time, making sure that you can turn the handlebars at least 45 degrees in each direction without having a cable under tension or without having the front wheels rub on any cable. Also check the chain line, ensuring that no cable is rubbing on the chain or any moving part. You can jack up the rear and test the shifting, or simply hit the road to see if everything is working the way it should. It's also a good idea to always check the front axle bolts before any ride, in case they have worked loose from excessive vibration. This photo of the complete StreetFox shows what can be done with a little hard work and some commonly available bicycle parts. This trike looks and rides as good as any commercially available trike, yet costs less than the shipping charge on a factory unit. Speed and braking are very good, and steering is comfortable and stable at any speed. Hill climbing is not a problem due to the full range of gearing, and the suspension makes for a very smooth ride. Most people who encounter the StreetFox think it was store-bought and give a strange look when told it was made using only hand tools and recycled bicycle parts. Riding a comfortable recumbent trike is so much easier on your body than an upright bicycle, so the long journeys are truly enjoyable. Once you get used to your new recumbent trike, you will wonder how you ever rode an upright bicycle for any real distance. Because you can ride in the most comfortable seated position with never a need to put your feet down, a recumbent trike is like your favorite living room chair, and the entire world is your television set. Often we ride our recumbent trikes to the beach or somewhere to have a picnic, and we never have to bring chairs along. We hope you enjoy building and riding your recumbent trike as much as we have. The results of your hard work will certainly be worth it, and nothing can compare to the feeling of riding your own quality-built DIY trike. Stop by the chopzone.com Builders Forum to share a photo of your work sometime, or if you just need some advice on your build. Thanks for your support and happy riding.